How much time would it actually take to reach each star in the Milky Way? Have you ever looked up at the night sky and wondered how long would it really take to get to the stars you see twinkling above? Not the nearest ones, not the bright ones. Every star in the Milky Way. Imagine travelling across 100,000 light years of swirling cosmic wonder, dodging deadly radiation, and drifting past billions of suns. Today, we're not just dreaming, we're calculating. From Voyager's snail-like pace to the mind-blowing speed of theoretical light sails, we'll uncover the truth, how long it would really take to reach the stars, and why some of them might be forever out of our grasp. Stay tuned. Understanding the scale. Before we talk about travel, engines, starships, or timelines measured in thousands or millions of years, we have to confront the single biggest obstacle to reaching the stars: distance. Not speed, not technology. Distance. Space is not just big, it is so large that the human brain is not naturally equipped to visualize it. Our instincts evolved to measure steps, roads, maybe oceans, but not trillions of miles of empty vacuum separating stars. So before we ask how long would it take to reach the stars, we need to understand how far away they truly are. On Earth, distance is intuitive. You know what a kilometre feels like. You know what a road trip feels like. You know what a flight across the ocean feels like. But in space, kilometres and miles stop being useful almost immediately. The distance from the Earth to the Moon, about 384,400 kilometres, already feels enormous. Yet that distance is nothing in cosmic terms. You could fit the distance from Earth to the Moon more than 380 times inside the distance from Earth to the Sun. The average distance between Earth and the Sun is called 1 astronomical unit, or 1 AU. That distance is about 149.6 million kilometres and 93 million miles. Light, moving at 300,000 kilometres per second, takes just over 8 minutes to travel from the Sun to Earth. That sounds fast, and it is. But this is where space begins to expose its true scale. The solar system is already vast. Now let's zoom out. The Sun is not alone. It is surrounded by planets, moons, asteroids, comets, and debris forming the solar system. The solar system doesn't end at Neptune. Beyond Neptune lies the Kuiper Belt, and far beyond that, the Oort cloud, a massive spherical shell of icy objects that may extend up to 100,000 astronomical units from the Sun. That means the outer edge of the solar system may stretch nearly halfway to the nearest star. To put that into perspective, Voyager 1, launched in 1977, travelling at over 17 kilometres per second, it has taken more than 45 years and is still not fully out of the solar system. This is just our local neighbourhood. We haven't even reached another star yet. Once we leave the solar system, kilometres and miles become meaningless. This is why astronomers use a different unit, the light year. A light year is not a measure of time, it is a measure of distance. It is the distance light travels in 1 year. Light moves at 299,792 kilometres per second. That's about 9.46 trillion kilometres per year, roughly 6 trillion miles per year. So when we say a star is 4 light years away, we mean the light leaving that star today will take 4 years to reach Earth. Even at the fastest speed possible in the universe, distance dominates everything. Let's make 1 light year relatable. Imagine shrinking the entire solar system so that the Sun is the size of a grain of sand. Earth is a microscopic speck orbiting it. In that scale model, the nearest star would be several kilometres away, nothing in between, just empty space. That emptiness is not an exaggeration. Space is mostly vacuum. The density between stars is so low that even travelling for years, you would rarely encounter a single atom. 1 light year is not just far, it is profoundly empty. Astronomers also use another unit, the parsec. A parsec is equal to 3.26 light years. That's about 19 trillion miles. The word comes from parallax second. a method used to measure stellar distances based on Earth's orbit around the Sun. Parsecs are especially useful for mapping the Milky Way. Distances within our galaxy are often measured in kiloparsecs, thousands of parsecs, megaparsecs, millions of parsecs used for other galaxies. The Milky Way is about 30 kiloparsecs across. That's 100,000 light-years from one side to the other. The nearest stars, shockingly far away. Now that we understand light-years, let's talk about the stars closest to us. The closest star to Earth, after the Sun, is Proxima Centauri. The distance is 4.24 light-years away. That doesn't sound far, but at human speeds, it's huge. At the speed of the fastest spacecraft ever built, it would take over 70,000 years to get there. Even if you could travel at 10 times that speed, it would still take thousands of years. And Proxima Centauri is our neighbour. Proxima Centauri is part of the Alpha Centauri system, which includes Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. It's 4.37 light-years away. This system is often discussed as humanity's first possible interstellar destination. Yet even here, the distance is so vast that no existing propulsion system makes the journey practical within a human lifetime. As we move farther out, the distances between stars increase dramatically. Some regions of the galaxy are relatively dense, others are cosmic deserts. Even within spiral arms, stars can be separated by dozens of light-years. This means reaching each star is not like hopping from stepping stone to stepping stone. It's more like crossing oceans of nothingness, over and over again. Now let's zoom out further. We don't live in an isolated group of stars. We live inside a galaxy. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure, spiral arms extending outward, a dense core, and a diffuse halo surrounding it all. When it comes to the size of the Milky Way, the diameter is 100,000 light-years. The thickness is 1,000 light-year, and the total stars is 100 to 400 billion. Even those numbers are estimates. We cannot see the entire Milky Way directly because we are inside it. Much of our understanding comes from infrared surveys, radio astronomy, and stellar motion tracking. At the centre of the Milky Way lies the galactic core. Its distance from Earth is 26,000 light-years. This region contains extremely dense star clusters, massive gas clouds, and the supermassive black hole Sagittarius A. Sagittarius A star has a mass over 4 million times that of the Sun. Stars near the core orbit at incredible speeds, some completing an orbit in just a few years. The Milky Way has several major spiral arms, including Perseus Arm, Scutum Centaurus Arm, Sagittarius Arm, and Orion Spur, where Earth is located. Earth sits in a relatively quiet region between major arms. Distances between arms can be thousands of light-years. Travelling from one spiral arm to another is not a short journey. It is a galactic expedition. Surrounding the disk is the galactic halo. This region contains ancient stars, globular clusters, and dark matter. Some halo stars orbit far above and below the galactic plane, reaching distances of tens of thousands of light-years. Distance is not just about how long a journey takes. Distance affects fuel requirements, energy needs, navigation accuracy, and communication delays. Even signals sent at light speed experience massive delays. A message sent from Earth to the galactic centre would take 26,000 years to arrive. No real-time control, no updates, no corrections. Once you leave, you are alone. Alpha Centauri is 4.37 light-years. The closest star system, still tens of thousands of years away at current speeds. Betelgeuse is 642 light-years, a red supergiant in Orion. So large it would engulf the orbit of Jupiter. Any spacecraft travelling at today's speeds would take millions of years to arrive. Galactic centre is 26,000 light-years. It has a dense, energetic, extreme environment. Travel times exceed civilizational timescales. When we talk about reaching each star in the Milky Way, we're not talking about a single journey. We're talking about hundreds of billions of destinations separated by vast emptiness. It's spread across a structure 100,000 light-years wide. Even if we could travel at a significant fraction of the speed of light, exploring the entire galaxy would take millions of years. This is not speculation. This is math. Understanding the scale of space reframes everything. It explains why interstellar travel is so rare in science fiction, grounded in realism. Robotic probes are favoured over human missions. Even nearby stars feel unreachable. Before engines, before starships, before ambition, distance decides what is possible. And in the Milky Way, distance is king. The limits of current human technology. When humanity talks about reaching the stars, the conversation almost always leaps ahead to futuristic engines, faster than light travel, or technologies that do not yet exist. But before any of that can be taken seriously, there is a more grounded and unavoidable question that must be answered first. What is the absolute fastest humanity has actually managed to move anything through space using real, tested, flown technology? The answer to that question defines the baseline reality of interstellar travel, because regardless of ambition, imagination, or funding, the universe only responds to what we can physically build and launch. Every spacecraft humanity has ever sent beyond Earth has relied on variations of the same fundamental principle: rockets that obey Newton's laws of motion. Whether powered by chemical reactions or gravitational slingshots, these vehicles are bound by limits that are not philosophical or technological shortcomings, but consequences of physics itself. To understand how long it would take to reach even the nearest star, we must examine these machines in detail, how fast they actually travel, and what those speeds mean once they leave the solar system behind. Human spaceflight began with chemical rockets, and despite decades of innovation, this remains the core technology that launches every spacecraft today. Chemical rockets work by expelling mass at high velocity in one direction, generating thrust in the opposite direction. The faster the exhaust velocity and the more mass expelled, the greater the thrust produced. However, this method carries a severe limitation. Fuel itself has mass, and carrying more fuel requires even more fuel to lift it, leading to rapidly diminishing returns. This exponential penalty is described by the rocket equation, and it is the fundamental reason why spacecraft speeds have not increased dramatically over time. The Apollo missions represent one of the most powerful applications of chemical rocketry ever achieved. The Saturn V rocket remains the most powerful rocket ever flown, capable of generating over 34 million newtons of thrust at liftoff. During the Apollo missions, astronauts travelled from Earth to the Moon at speeds that peaked around 10.8 kilometres per second relative to Earth, which was sufficient to escape Earth's gravity and enter lunar transfer orbit. While this speed was extraordinary by human standards, it was still modest on an interplanetary scale and completely negligible when compared to interstellar distances. Once Apollo spacecraft reached the Moon, they did not continue accelerating indefinitely. Chemical rockets are designed to burn for a limited time, after which the spacecraft coasts along a trajectory determined by gravity and initial velocity. This means that while Apollo missions demonstrated the ability to leave Earth and reach another celestial body, they also illustrated a critical reality. Chemical propulsion does not allow for sustained acceleration over long periods. Once the engines shut down, the spacecraft is effectively locked into its speed, unable to make meaningful increases without carrying impractically large amounts of additional fuel. As robotic exploration replaced crewed deep space missions, humanity began to push spacecraft farther and faster, not by inventing new propulsion systems, but by using gravity itself as a tool. Gravity assist maneuvers, also known as slingshot maneuvers, allow spacecraft to steal a small amount of momentum from planets as they pass by, increasing their speed without burning fuel. This technique has been used extensively in interplanetary missions and represents one of the most important speed-enhancing strategies available with current technology. The Voyager missions are the clearest and most extreme example of what gravity-assisted chemical spacecraft can achieve. Launched in 1977, Voyager 1 and Voyager 2 were designed to take advantage of a rare planetary alignment that allowed them to visit multiple outer planets using successive gravity assists. As Voyager 1 passed by Jupiter and Saturn, it gained speed with each encounter, eventually reaching a heliocentric velocity of approximately 17 kilometers per second, or about 61,000 kilometers per hour. This speed is not theoretical. It has been measured, tracked and maintained for decades. Voyager 1 is, as of now, the fastest human-made object ever to leave the solar system. It has crossed the heliopause, entered interstellar space, and continues to travel outward, sending back faint signals that take over 22 hours to reach Earth. Yet despite this extraordinary achievement, Voyager's velocity highlights just how constrained current technology truly is. At 17 kilometers per second, Voyager 1 covers about 536 million kilometers per year. That sounds impressive until it is compared with interstellar distances. The nearest star system, Alpha Centauri, is approximately 4.37 light-years away, which corresponds to roughly 41 trillion kilometers. Dividing that distance by Voyager's speed yields a travel time of approximately 73,000 years. This calculation assumes uninterrupted travel at constant speed, no deceleration and no obstacles, which means it represents an optimistic lower bound rather than a realistic mission profile. 73,000 years is not an abstract number. It is longer than the entire history of agriculture, longer than the existence of written language, and longer than Homo sapiens have been anatomically modern. If Voyager 1 had been launched at the dawn of civilization, it would still be tens of thousands of years away from reaching Alpha Centauri today. This single calculation alone defines the practical boundary of current human propulsion technology when applied to interstellar travel. The New Horizons mission provides another useful benchmark. Launched in 2006 to study Pluto and the Kuiper Belt, New Horizons was the fastest spacecraft ever launched from Earth, reaching a departure speed of approximately 16.26 kilometers per second relative to Earth. Using a powerful Atlas V rocket and a gravity assist from Jupiter, New Horizons completed its journey to Pluto in just under a decade, a remarkable achievement given Pluto's average distance of nearly 6 billion kilometers from the Sun. However, New Horizons' speed advantage over Voyager is marginal on interstellar scales. Even at its peak velocity, the difference between 16 and 17 kilometers per second is insignificant when distances are measured in trillions of kilometers. If New Horizons were aimed toward Alpha Centauri instead of Pluto, it would still require more than 80,000 years to arrive. The slight increase in launch velocity does not fundamentally change the outcome, because chemical propulsion remains bound by the same energy constraints. What makes these speeds particularly limiting is that they are achieved only briefly. Most spacecraft do not accelerate continuously. Instead, they receive a single burst of acceleration during launch, followed by occasional course corrections. Gravity assists can add incremental speed, but only when suitable planets are available and properly aligned. Once a spacecraft leaves the planetary region of the solar system, there are no additional opportunities for gravitational acceleration. The craft then coasts indefinitely, its velocity effectively frozen in time. This leads to another critical limitation of current technology: deceleration. Even if a spacecraft could reach another star in tens of thousands of years, it would arrive at full cruising speed with no practical way to slow down. Chemical rockets cannot carry enough fuel to decelerate after such a journey, and gravity assists are impossible in an unknown star system without prior infrastructure or precise navigation. This means that under current propulsion models, interstellar spacecraft would not arrive in a condition suitable for exploration. They would simply pass through the target system at extreme speed, unable to stop. Communication also becomes increasingly impractical at these distances. Voyager's signals are detected using some of the most sensitive antennas ever built, and even then, data rates are measured in bits per second. At interstellar distances, signal strength drops according to the inverse square law, meaning that each doubling of distance reduces signal strength by a factor of 4. By the time a spacecraft reaches even the nearest star, maintaining communication using current transmitters and power sources would be extraordinarily difficult, if not impossible. Another constraint imposed by current rocket technology is durability over time. Voyager spacecraft were designed for missions lasting a few years, yet they have survived for decades due to careful engineering and redundancy. However, a mission lasting tens of thousands of years would require systems capable of functioning far beyond any tested lifespan. Materials degrade, electronics fail, power sources decay, and even the most robust designs cannot be guaranteed to operate indefinitely. Chemical propulsion does not merely limit speed. It locks missions into timeframes that exceed the durability of known engineering systems. Even navigation becomes a challenge over such extended journeys. Interstellar space is not entirely empty. Dust particles, radiation, and micrometeoroids pose cumulative risks over thousands of years. At speeds of 17 kilometers per second, even microscopic particles can cause damage over time. Current spacecraft are shielded for decades-long missions, not for continuous exposure across millennia. When all these factors are combined, limited acceleration, finite maximum speed, lack of deceleration capability, communication delays, system degradation, and environmental hazards, it becomes clear that current human technology is not merely slow, but fundamentally mismatched to the scale of interstellar space. Rockets like those used in Apollo, Voyager, and New Horizons represent the absolute peak of what chemical propulsion combined with gravity assists can achieve. And that peak still leaves humanity confined to its immediate stellar neighbourhood in purely theoretical terms. The numbers themselves are unforgiving. At 17 kilometers per second, travelling 1 light year takes approximately 18,000 years. Reaching Alpha Centauri requires more than 4 of those light years. Travelling to more distant stars increases the time linearly, but the implications grow exponentially when compounded with system reliability and communication challenges. A star 100 light-years away would require nearly 2 million years of travel at Voyager speeds. A star near the galactic centre would require hundreds of millions of years. These are not estimates meant to discourage ambition. They are direct consequences of measured velocities and known distances. Every calculation begins with the same starting point. How fast can we go right now using machines we know how to build? As long as that answer remains in the range of tens of kilometers per second, interstellar travel remains an exercise in geological and evolutionary timescales, rather than human ones. Current rocket technology has allowed humanity to explore the solar system in extraordinary detail, revealing worlds of ice, rock and gas with astonishing complexity. But the moment those same rockets are pointed toward the stars, their limitations become impossible to ignore. The gap between planetary exploration and interstellar travel is not a matter of refinement or incremental improvement. It is a gulf defined by physics, energy, and time. Theoretical propulsion and the hard limits of physics. Once the limitations of chemical rockets are fully understood, it becomes clear that no incremental improvement to existing launch systems will ever make interstellar travel practical. Even the fastest spacecraft humanity has ever built remain locked into speeds that make the nearest stars effectively unreachable within any reasonable time frame. This realization has driven scientists and engineers to explore propulsion concepts that fundamentally differ from chemical combustion. Concepts designed not to escape gravity wells more efficiently, but to sustain acceleration over long periods, or to reach velocities that chemical rockets cannot approach. These ideas fall into the category of theoretical propulsion, meaning they are rooted in established physical laws, but remain either untested, partially demonstrated, or far beyond current engineering capabilities. The defining challenge of interstellar propulsion is not simply achieving high speed, but doing so without carrying vast quantities of fuel that negate the benefits of acceleration. This is why nearly every serious proposal for interstellar travel moves away from traditional rocket exhaust and towards systems that either minimize reaction mass, generate energy far more efficiently, or bypass conventional propulsion entirely. Among these concepts, ion drives represent the most mature and operational technology. Nuclear propulsion occupies a transitional zone between theory and feasibility, and light sails represent an entirely different paradigm, in which the spacecraft does not carry fuel at all. Beyond these, concepts like faster-than-light travel, wormholes, and space-time manipulation exist only as mathematical possibilities, constrained by extreme energy requirements and unresolved physical contradictions. Ion propulsion represents a fundamental shift away from high-thrust, short-duration propulsion toward extremely low thrust, applied continuously over long periods of time. Unlike chemical rockets, which expel large quantities of propellant at moderate exhaust velocities, ion drives expel very small amounts of propellant at extremely high exhaust velocities, often exceeding 30 kilometers per second. The trade-off is clear. Ion engines cannot lift spacecraft off planetary surfaces or perform rapid maneuvers. But once in space, they can accelerate a spacecraft for months or even years without interruption. The most prominent real-world example of ion propulsion is NASA's Dawn spacecraft, launched in 2007 as part of the Discovery program. Dawn was equipped with 3 xenon-fueled ion thrusters and was designed to study 2 large bodies in the asteroid belt, Vesta and Sirius, in a single mission. This alone was unprecedented, as chemical propulsion would have required far more fuel to enter orbit around 2 separate targets. Dawn's ion engines operated by ionizing xenon gas and accelerating the ions through an electric field, producing a gentle but continuous thrust that gradually increased the spacecraft's velocity over time. Although Dawn's instantaneous acceleration was almost imperceptible, amounting to roughly the force of a sheet of paper resting on a human hand, the cumulative effect was significant. Over the course of its mission, Dawn achieved a total velocity change of more than 11 kilometers per second, exceeding that of many chemically propelled spacecraft. What made this possible was not raw power, but endurance. Ion drives allow spacecraft to keep accelerating long after chemical rockets have exhausted their fuel, effectively trading patience for efficiency. Despite this advantage, ion propulsion does not solve the interstellar travel problem. While ion drives can produce higher total velocity changes over time, their acceleration remains extremely low. Even if an ion-powered spacecraft were allowed to accelerate continuously for decades, it would still fall far short of relativistic speeds. Power generation is the primary limiting factor, as ion engines require substantial electrical energy, typically supplied by solar panels or nuclear power sources. As a spacecraft moves farther from the Sun, solar power becomes ineffective, and nuclear power systems capable of sustaining multi-decade thrust at high levels remain unproven. In practical terms, ion propulsion could reduce interstellar travel times by a modest factor compared to chemical rockets, but not by orders of magnitude. A spacecraft equipped with advanced ion engines might reach velocities of tens or possibly hundreds of kilometers per second, which would still require thousands of years to reach the nearest stars. Ion drives represent an evolutionary improvement in efficiency, not a revolutionary breakthrough in speed. Nuclear thermal propulsion, harnessing atomic energy for thrust. Nuclear thermal propulsion occupies a middle ground between existing technology and speculative engineering. Unlike ion drives, which rely on electricity to accelerate ions, nuclear thermal rockets use nuclear reactions directly to heat propellant, typically hydrogen, which is then expelled at high velocity to generate thrust. The advantage of this approach lies in the enormous energy density of nuclear fuel compared to chemical propellants. Nuclear reactions release millions of times more energy per unit mass than chemical reactions, allowing for much higher exhaust velocities and greater efficiency. The concept of nuclear thermal propulsion is not hypothetical in principle. During the 1960s and early 1970s, the United States conducted extensive testing under the NERVA, Nuclear Engine for Rocket Vehicle Application program. These engines demonstrated exhaust velocities roughly twice that of the best chemical rockets, translating to significantly higher achievable spacecraft speeds. Had the program continued, nuclear thermal rockets could have enabled fast missions to Mars and the outer planets. However, even with this improvement, nuclear thermal propulsion does not enable rapid interstellar travel. Doubling or tripling exhaust velocity reduces travel times by a corresponding factor, but when initial timescales are measured in tens of thousands of years, such improvements remain insufficient. A nuclear thermal spacecraft travelling at several dozen kilometres per second would still require thousands of years to reach Alpha Centauri. The technology improves feasibility within the solar system and perhaps shortens interstellar probe missions to generational timescales, but it does not collapse distances into human lifetimes. Nuclear fusion propulsion represents a more ambitious extension of nuclear concepts. Fusion reactions, which power stars themselves, offer even greater energy density than fission-based nuclear thermal rockets. In theory, fusion-powered spacecraft could achieve exhaust velocities measured in thousands of kilometres per second, potentially reaching a few % of the speed of light. Projects such as Project Daedalus and Project Icarus have explored the feasibility of fusion-driven interstellar probes using pellets of fusion fuel ignited by powerful lasers or particle beams. Despite their theoretical promise, fusion propulsion systems face enormous engineering challenges. Controlled fusion remains difficult even in stationary reactors on Earth, let alone in compact, reliable systems suitable for spacecraft. Fuel containment, ignition stability, heat management, radiation shielding, and long-term system reliability all present unresolved problems. Even if these challenges were overcome, fusion-powered spacecraft would still operate within relativistic limits, meaning that while travel times could be reduced to decades or centuries, they would not approach instantaneous or faster-than-light travel. One of the most radical departures from conventional propulsion is the Breakthrough Starshot Initiative, a privately funded research program aimed at developing ultralight spacecraft propelled by light itself. The core idea is deceptively simple. Instead of carrying fuel, a spacecraft could be pushed by photons emitted from a powerful Earth-based laser array. This method relies on the momentum carried by light, which, while extremely small per photon, can exert a measurable force when applied continuously to a reflective surface. The Starshot concept envisions a fleet of gram-scale probes attached to thin, reflective light sails, accelerated by a multi-gigawatt laser system to speeds approaching 20% of the speed of light. At this velocity, a spacecraft could reach the Alpha Centauri system in approximately 20 years, with data transmission back to Earth taking an additional 4 years. This would represent the first realistic interstellar mission within a human lifetime. Unlike chemical or nuclear propulsion, light sails do not suffer from the rocket equation, as they do not carry propellant. All energy is supplied externally, allowing the spacecraft to remain extremely lightweight. However, this advantage comes with severe constraints. The required laser infrastructure would need to generate sustained power output comparable to that of the largest power plants on Earth, focused with extraordinary precision over millions of kilometres. Maintaining beam coherence, preventing sail damage and ensuring accurate targeting present unprecedented technical challenges. Furthermore, light sail propulsion provides no means of deceleration once the spacecraft reaches its destination. The probe would pass through the target star system at relativistic speed, limiting observation time to mere hours or days. Communication back to Earth would require transmitting signals from a power source smaller than a light bulb across interstellar distances, pushing the limits of detectability. Breakthrough starshot remains a concept rather than a mission, but it is grounded in known physics and does not require speculative particles or violations of physical law. It represents the closest humanity has come to a credible plan for near-relativistic interstellar travel, yet even this approach is constrained by immense energy requirements and engineering uncertainties. At the heart of every discussion about interstellar travel lies the speed of light, approximately 299,792 kilometers per second. According to Einstein's theory of special relativity, this speed is not merely a technological limit, but a fundamental property of space-time itself. As an object with mass accelerates toward the speed of light, its relativistic mass increases, requiring exponentially more energy to continue accelerating. Reaching the speed of light would require infinite energy, making it physically impossible for any object with mass. This limitation is not theoretical speculation, but a consequence of well-tested physics confirmed by countless experiments. Particle accelerators routinely push subatomic particles to velocities approaching the speed of light, and the energy required to achieve even small increases in speed grows dramatically as this limit is approached. Scaling this behavior up to macroscopic spacecraft reveals the enormity of the challenge. Accelerating even a small spacecraft to relativistic speeds would require energy on the scale of planetary power generation. Time dilation, another consequence of relativity, does not eliminate this problem. While travelers moving at near-light speeds would experience time passing more slowly relative to observers on Earth, the energy cost of achieving and maintaining such speeds remains prohibitive. Relativity allows for interesting effects, but it does not provide shortcuts or loopholes that enable faster-than-light travel. Beyond propulsion systems that operate within conventional space-time, some theories propose altering space-time itself to allow rapid travel between distant regions of the universe. Wormholes are hypothetical tunnels through space-time that could, in principle, connect two distant points directly. While solutions to Einstein's field equations permit the existence of wormholes, maintaining a stable, traversable wormhole would require exotic matter with negative energy density, something that has never been observed and may not exist in usable quantities. Even if such matter were available, the energy required to create and stabilize a wormhole would likely exceed the total output of entire stars. Additionally, wormholes raise unresolved issues related to causality, stability, and quantum effects that could render them inherently unstable or untraversable. The Alcubierre drive represents another speculative approach, proposing a method of faster-than-light travel by contracting space-time in front of a spacecraft and expanding it behind, effectively moving the spacecraft without locally exceeding the speed of light. While mathematically consistent within general relativity, the Alcubierre metric requires enormous amounts of negative energy, far beyond anything that could be generated or controlled with known physics. Subsequent refinements have reduced the theoretical energy requirements, but they remain astronomically large and rely on forms of matter that have no known physical counterpart. Both wormholes and warp drives remain mathematical curiosities rather than engineering proposals. They highlight the flexibility of space-time equations, but do not offer practical pathways for interstellar travel. No experimental evidence suggests that these methods can be realized, and they remain firmly outside the realm of feasible technology. Taken together, these propulsion concepts illustrate the full spectrum of human thinking about interstellar travel, from incremental improvements like ion drives to radical reimaginings like light sails and space-time manipulation. Each approach is constrained by the same underlying reality. Energy, mass, and the structure of space-time impose limits that cannot be ignored or bypassed through clever engineering alone. Ion drives show that sustained acceleration can outperform brute force, but they remain too slow for interstellar journeys. Nuclear propulsion promises greater speeds, but still operates within time frames measured in centuries or longer. Light sails offer the first credible path to relativistic travel, but demand infrastructure and precision on an unprecedented scale. Faster-than-light concepts remain mathematically intriguing, but physically unattainable with current understanding. Nearest stars, the realistic targets. When the discussion of interstellar travel shifts from theory to plausibility, the conversation narrows rapidly, not because of a lack of ambition, but because of the unforgiving structure of our stellar neighbourhood. Among the hundreds of billions of stars in the Milky Way, only a handful exist close enough to even be considered potential destinations using foreseeable technology. These stars are not nearby in any everyday sense of the word, but relative to the immense scale of the galaxy, they form a small cluster of reachable targets that define the outer boundary of realistic interstellar exploration. At the centre of this group lies the Alpha Centauri system, a collection of stars that has shaped humanity's understanding of stellar distances, planetary systems beyond our own, and the practical limits of travel beyond the solar system. The Alpha Centauri system is not a single star, but a gravitationally bound stellar system consisting of three known stars: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Located approximately 4.37 light-years from Earth, this system has long been recognised as the nearest stellar neighbour to the Sun, making it the natural focal point for any serious discussion of interstellar travel. Its proximity has made it one of the most intensely studied star systems in the night sky, observed continuously for centuries and scrutinised with every major advance in astronomical instrumentation. The discovery history of Alpha Centauri begins long before the development of modern astronomy, as its brightest components are visible to the naked eye from the southern hemisphere. Ancient observers would have seen Alpha Centauri as a single point of light, unaware that it was in fact a complex stellar system. The system was first identified as a binary star by French astronomer Jean-Baptiste Louis de Lacaille in the mid-18th century during his expedition to the Cape of Good Hope. Lacaille catalogued Alpha Centauri as a double star, noting subtle changes in position that suggested orbital motion. This marked the beginning of systematic study into the system's structure. Throughout the 19th century, astronomers refined their measurements of Alpha Centauri's orbit, determining that Alpha Centauri A and B form a tight binary pair, orbiting a common centre of mass with a period of approximately 79.9 years. These two stars are remarkably similar to the Sun in mass, luminosity and spectral type, particularly Alpha Centauri A, which is often described as a near-solar twin. Alpha Centauri B, while slightly smaller and cooler, still falls within the range of stars considered broadly Sun-like, making the system especially intriguing from the standpoint of planetary formation and habitability. The third member of the system, Proxima Centauri, remained undiscovered until 1915, when Scottish astronomer Robert Innes identified it as a faint red dwarf star with an unusually large proper motion. Proxima Centauri was later confirmed to be gravitationally bound to Alpha Centauri A and B, though it orbits at a much greater distance, estimated at roughly 13,000 astronomical units. This wide separation means that while Proxima Centauri is physically associated with the system, its orbital period around the central binary may span hundreds of thousands of years. Proxima Centauri's significance lies not only in its proximity to Earth, at approximately 4.24 light-years, but also in its classification as a red dwarf star, the most common type of star in the Milky Way. Red dwarfs are smaller, cooler, and far less luminous than Sun-like stars, but they burn their fuel much more slowly, granting them lifespans measured in trillions of years. Because of their abundance and longevity, red dwarfs have become central to discussions of habitability beyond the solar system, and Proxima Centauri offers the closest opportunity to study such a star in detail. The discovery of Proxima Centauri b in 2016 dramatically intensified scientific and public interest in the Alpha Centauri system. Detected using the radial velocity method, Proxima b is an exoplanet with a minimum mass approximately 1.17 times that of Earth, orbiting Proxima Centauri at a distance of about 0.05 astronomical units. Despite its close orbit, Proxima b resides within the star's habitable zone, the region where temperatures could allow liquid water to exist on the planet's surface under the right atmospheric conditions. The proximity of Proxima b to its star raises significant challenges for habitability, including tidal locking, stellar flares, and high levels of radiation, as red dwarfs are known for their magnetic activity. Proxima Centauri frequently emits powerful flares capable of stripping atmospheres and exposing planetary surfaces to intense radiation. However, the mere existence of a potentially rocky planet in the habitable zone of the nearest star system has made Proxima b one of the most important exoplanets ever discovered, as it represents a tangible target for future interstellar probes. Alpha Centauri A and B have also been the subject of extensive searches for exoplanets, though results have been more tentative. Claims of Earth-mass planets orbiting Alpha Centauri b have been debated and retracted, highlighting the difficulty of detecting small planets in binary systems. Nonetheless, the system remains a prime candidate for hosting additional planets, and ongoing observational campaigns continue to refine our understanding of its architecture. From the perspective of interstellar travel, the Alpha Centauri system represents both a tantalizing opportunity and a sobering benchmark. At a distance of 4.37 light-years, it is close enough that meaningful comparisons between propulsion methods can be made, yet far enough that even the most optimistic scenarios reveal immense challenges. Using current human technology, exemplified by Voyager, one's velocity of approximately 17 kilometers per second, the journey to Alpha Centauri would require roughly 73,000 years. This calculation assumes uninterrupted travel at constant speed, no deceleration, and no system failures, conditions that are idealized and unlikely in practice. Even if modest improvements in propulsion efficiency were achieved through advanced ion drives or nuclear thermal propulsion, travel times would remain measured in thousands to tens of thousands of years. A spacecraft traveling at 100 kilometers per second, far beyond what has been achieved to date, would still take over 13,000 years to reach Alpha Centauri. These timescales extend far beyond any individual human lifespan, and even beyond the continuity of known civilizations, placing such missions firmly in the realm of multi-generational or autonomous robotic exploration. Theoretical propulsion systems offer more dramatic reductions in travel time, but even these underscore the scale of the challenge. A fusion-powered spacecraft capable of reaching 1% of the speed of light would complete the journey in approximately 437 years, not accounting for acceleration and deceleration phases. While this represents a monumental improvement, it still implies a mission lasting several centuries, requiring technologies capable of functioning reliably over timescales far longer than any existing space mission. Near-light-speed propulsion, such as that proposed by the Breakthrough Starshot initiative, fundamentally alters the equation. At 20% of the speed of light, a light sail-driven probe could reach Alpha Centauri in roughly 22 years, making it the first plausible interstellar mission within a single human lifetime. However, this approach introduces new constraints, including extreme acceleration forces, vulnerability to interstellar dust, limited payload mass, and the inability to decelerate upon arrival. Such probes would function as high-speed flyby missions rather than explorers capable of extended study. Time dilation effects become significant at relativistic speeds, but they do not eliminate the engineering challenges associated with acceleration, energy supply, and communication. Even at 20% of light speed, relativistic effects are modest, and the journey remains constrained by the need to survive decades of exposure to cosmic radiation and interstellar particles. Moreover, transmitting data back to Earth from a probe of such small mass would require breakthroughs in communication technology and signal processing. Despite these challenges, Alpha Centauri remains the most realistic interstellar target precisely because it allows meaningful trade-offs between speed, payload, and mission duration to be explored quantitatively. It serves as a test case against which every propulsion concept can be measured, revealing which ideas reduce travel time by meaningful margins, and which merely shift the problem without solving it. The system's proximity also makes it a critical benchmark for astrobiology and planetary science. If life exists anywhere beyond the solar system, Alpha Centauri is among the most likely places to find it, not because it is inherently special, but because it is accessible enough to be studied in detail using both remote sensing and, eventually, direct exploration. High-resolution imaging of Proxima b and any planets orbiting Alpha Centauri, A and B, remains a major goal of future space telescopes, as such observations could reveal atmospheric composition, surface conditions, and potential biosignatures. In the broader context of the Milky Way, Alpha Centauri illustrates the stark reality of interstellar distances. If reaching the nearest star system requires decades at relativistic speeds or tens of thousands of years at conventional velocities, then extending exploration to dozens, hundreds, or thousands of stars becomes a task spanning geological or cosmic timescales. This does not diminish the scientific value of such exploration, but it reframes it as a long-term endeavour measured in generations rather than missions. The Alpha Centauri system is not merely a destination, it is a boundary marker. It defines the transition point between planetary exploration, which humanity has already mastered in principle, and true interstellar travel, which remains at the edge of feasibility. Every calculation of travel time, every assessment of propulsion capability, and every discussion of mission design ultimately circles back to this system, because it represents the closest test of whether humanity can extend its reach beyond the Sun's gravitational influence and into the domain of other stars. Barnard's star, the fast-moving neighbour. Among the stars closest to the solar system, Barnard's star occupies a unique and scientifically important position, not because it is the nearest, nor because it is the brightest, but because it reveals how deceptive proximity can be when measured on interstellar scales. Located at a distance of approximately 5.96 light-years from Earth, Barnard's star is the fourth closest known individual star to the Sun after the Alpha Centauri system and Proxima Centauri. While this distance places it firmly within humanity's immediate stellar neighbourhood, it remains far enough away that even the most optimistic propulsion concepts struggle to reduce travel times to manageable scales. Its importance, however, lies not only in its distance, but in the story of its discovery, its extraordinary motion through space, and its role as one of the most closely scrutinized stars in the search for planets beyond the solar system. Barnard's star is a red dwarf, classified as a spectral type M4 star, meaning it is significantly smaller, cooler, and less luminous than the Sun. Red dwarfs dominate the stellar population of the Milky Way, accounting for approximately 70 to 75% of all stars. Yet their intrinsic faintness makes them difficult to detect at large distances. Barnard's star is only visible through a telescope despite its proximity, underscoring a fundamental truth of stellar astronomy. Closeness does not guarantee visibility, and the night sky is biased toward luminous stars rather than nearby ones. This faintness also meant that Barnard's star remained undiscovered until the late 19th century, long after more distant but brighter stars had been catalogued. The star is named after Edward Emerson Barnard, an American astronomer whose career exemplified the transition from classical visual astronomy to modern astrophysics. Barnard discovered the star in 1916 while working at Yerkes Observatory, using photographic plates to examine regions of the sky over time. What caught his attention was not the star's brightness, but its exceptionally high proper motion, meaning its apparent movement across the sky relative to background stars. Barnard measured a proper motion of approximately 10.3 arcseconds per year, the largest known for any star at the time, and still the highest recorded proper motion of any known star. This rapid motion immediately marked Barnard's star as extraordinary. Proper motion is a key indicator of proximity, because nearby stars appear to move more quickly against the distant stellar background as Earth orbits the Sun. Barnard's precise measurements confirmed that the star was extremely close by astronomical standards, prompting further study to determine its distance through parallax measurements. These measurements revealed that Barnard's star lay just under 6 light-years away, placing it among the Sun's closest neighbours and cementing its place as a cornerstone object in the study of nearby stars. The significance of Barnard's star's proper motion extends beyond its discovery. The star is moving through the Milky Way at a velocity of approximately 140 kilometers per second relative to the Sun, an unusually high speed compared to most nearby stars. This suggests that Barnard's star may belong to an older population of stars known as the galactic halo or thick disk, rather than the thin disk where the Sun resides. Its high velocity implies a long and complex orbital history around the galactic center, potentially spanning billions of years and multiple passages through the dense inner regions of the Milky Way. Physically, Barnard's star is a small object with a mass estimated at about 14% that of the Sun and a radius of roughly 20% of the Sun's radius. Its surface temperature is approximately 3,100 Kelvin, far cooler than the Sun's 5,778 Kelvin, resulting in a dim, reddish glow dominated by infrared emission. The star's total luminosity is only about 0.0035% of the Sun's, meaning that even planets orbiting very close to the star receive modest amounts of energy. This low luminosity has direct implications for the potential habitability of any planets orbiting Barnard's star. The habitable zone, defined as the region where liquid water could exist on a planet's surface, lies extremely close to the star, at distances of just 0.04 to 0.1 astronomical units. At such close ranges, planets would likely be tidally locked, with one hemisphere permanently facing the star while the other remains in perpetual darkness. While this configuration does not rule out habitability outright, it introduces challenges related to atmospheric circulation, temperature extremes, and radiation exposure. Barnard's star has been a prime target in the search for exoplanets for decades, largely because its proximity allows for extremely precise measurements of stellar motion. Small planets exert gravitational tugs on their host stars, causing subtle wobbles that can be detected using the radial velocity method. Because Barnard's star is both nearby and relatively low mass, the gravitational influence of orbiting planets would be more pronounced than around larger stars, making detection theoretically easier. Throughout the 20th century, Barnard's star became the subject of repeated claims of planetary companions, none of which withstood scrutiny. One of the most famous episodes occurred in the 1960s, when astronomer Peter van der Kamp announced the detection of a planetary system around Barnard's star based on astrometric measurements. These claims suggested the presence of multiple Jupiter-mass planets, sparking excitement about the possibility of nearby worlds. However, subsequent analysis revealed that the observed stellar motion was an artifact caused by changes in the telescope optics, not the gravitational influence of planets. This episode became a cautionary tale in astronomy, highlighting the difficulty of detecting exoplanets and the importance of independent verification. The search for planets around Barnard's star continued into the era of high-precision spectroscopy. Advances in instrumentation allowed astronomers to measure stellar radial velocities with unprecedented accuracy, down to variations of less than 1 meter per second. In 2018, an international team of astronomers announced the detection of a candidate planet, Barnard's star B, based on long-term radial velocity observations collected over 2 decades. The proposed planet was estimated to have a minimum mass of about 3.2 Earth masses and an orbital period of approximately 233 days, placing it well outside the star's habitable zone. Barnard's star B, if confirmed, would be classified as a cold super-Earth, receiving only a small fraction of the energy Earth receives from the Sun. Surface temperatures would likely be far below freezing, making the planet inhospitable to life as we know it. However, the detection itself was significant, as it demonstrated the ability to identify relatively low-mass planets around nearby red dwarfs using current technology. The planet's existence remains the subject of ongoing study, with some analyses questioning the signal's robustness. But the evidence highlights the complexity of planetary systems around even the simplest stars. Beyond individual planet detections, Barnard's star has also been studied for circumstellar dust and debris, which could indicate the presence of asteroid belts or remnants of planet formation. Observations in the infrared and submillimeter wavelengths have placed constraints on the amount of dust in the system, suggesting that if such structures exist, they are relatively sparse. This may reflect the star's age, estimated to be between 7 and 12 billion years, making it significantly older than the Sun. Over such long timescales, debris disks can dissipate, and planetary systems can undergo substantial dynamical evolution. The age of Barnard's star is a crucial factor in assessing its planetary potential. Older stars have had more time for planetary systems to stabilize, but they may also host planets that have lost atmospheres or experienced dramatic climatic changes. Additionally, red dwarfs are known to be highly active during their early lifetimes, emitting intense ultraviolet and X-ray radiation that can strip planetary atmospheres. While Barnard's star is relatively quiet today, its early history may have been hostile to the development of life on nearby planets. From an interstellar exploration perspective, Barnard's star represents a compelling but challenging target. Its distance of nearly 6 light-years places it just beyond the Alpha Centauri system, meaning that travel times increase significantly even for near-relativistic probes. At Voyager, one speed of approximately 17 kilometers per second, a journey to Barnard's star would require roughly 105,000 years, assuming constant velocity and no deceleration. Even at 10% of the speed of light, travel would take nearly 60 years, excluding acceleration and deceleration phases. Despite these daunting timescales, Barnard's star remains one of the most realistic candidates for future interstellar exploration, precisely because it is close enough to allow detailed remote study and potentially reachable by advanced probe concepts. Its high proper motion also means that its position in the sky changes noticeably over time, providing a dynamic laboratory for testing models of stellar kinematics and galactic structure. In the broader context of nearby stars, Barnard's star illustrates an essential truth about the solar system's neighborhood. Proximity does not equate to simplicity, and even the closest stars can host complex histories, ambiguous planetary systems, and environments very different from our own. The star's faintness, age, and high-velocity challenge assumptions about what nearby stars are like and underscore the diversity of stellar systems within just a few light-years of Earth. When humanity looks outward into the galaxy, our perception of nearby space is shaped not by brightness, but by distance. To the unaided eye, the night sky is dominated by stars that shine most brilliantly, not necessarily those closest. Within about 10 light-years of Earth, a vast array of stellar neighbours exists, each with its own story, physical characteristics, and scientific value. Among these are Wolf 359, Lalande 21185, Sirius, and Luyten star, stars that represent the diversity of stellar types, observational history, and the evolving search for planets beyond our solar system. These stars are often overshadowed in the public imagination by Alpha Centauri or Barnard star, yet their physical properties and scientific narratives offer a deeper understanding of the immediate cosmic environment surrounding the Sun. In this chapter, we will explore each of these stars in depth, not only as coordinates in space, but as objects with histories, discoveries, modern observations, and, in a few cases, tantalizing hints of planets that might orbit them. Wolf 359, a dim beacon with a rich scientific legacy. Wolf 359 is among the closest stars to Earth, yet it is invisible to the unaided eye, a startling reminder that proximity does not guarantee visibility in astronomy. Located at a distance of approximately 7.78 light-years, Wolf 359 was discovered relatively recently in astronomical terms, and its faintness makes it an archetype of the most common stars in our galaxy, red dwarfs. The star is named after Maximilian Franz Joseph Cornelius Wolf, a German astronomer whose work in the early 20th century advanced stellar cataloguing and variable star discovery. Wolf compiled an extensive list of stars with high proper motion, a technique that identifies nearby stars by their apparent motion against more distant background stars over time. Proper motion is a key tool in the discovery of nearby stars, and Wolf 359's significant motion made it stand out to astronomers despite its low luminosity. Wolf 359 is a red dwarf of spectral class M6, meaning it is much cooler and smaller than the Sun. Its surface temperature is roughly 2,800 Kelvin, less than half that of the Sun, and its total luminosity is only a few thousandths that of our star. For this reason, even though Wolf 359 lies within 10 light-years, it can only be observed through powerful telescopes. In fact, its very discovery came from photographic plates and motion studies, not direct naked-eye observation. One of the most remarkable aspects of Wolf 359 is its intense magnetic activity. Like many red dwarfs, Wolf 359 exhibits frequent stellar flares, sudden eruptions of radiation and particles driven by magnetic field reconnections in the star's atmosphere. These flares can be powerful enough to briefly increase the star's brightness by factors of several times, albeit still faint compared to brighter stars. This activity is of exceptional interest to astrophysicists because it reveals how magnetism and stellar dynamics operate in stars with convective interiors. Convective interiors, the turbulent mixing of gas that carries energy from a star's core to its surface, characterize low-mass stars like Wolf 359, and they are believed to be responsible for super-strong magnetic fields compared to stars like the Sun. The flares seen on Wolf 359 can be hundreds of times more energetic than typical solar flares. From an exoplanet perspective, this activity represents a challenge. Any planet orbiting close enough to Wolf 359 to lie in its habitable zone would also have to endure intense bursts of radiation, posing questions about atmosphere loss and surface conditions. Despite extensive observation, no confirmed planets have yet been identified around Wolf 359. Several searches, including radial velocity and transit surveys, have looked for periodic signals that would indicate orbiting planets, but none have produced robust detections. This is not surprising, given the relatively small size of the star, combined with the limitations of current instrumentation when observing faint red dwarfs. However, Wolf 359 remains a prime target for future missions designed to probe low-mass stars for terrestrial worlds. Wolf 359 has also entered popular culture, most notably as a location in science fiction. Its inclusion in a famous episode of a well-known space opera franchise brought its name into the public imagination, albeit fictionalized with dramatic battles and high stakes. That narrative choice reflects a deeper truth. Nearby stars capture our imagination not because they are bright, but because they are the first rung on the ladder of interstellar exploration. From a scientific perspective, Wolf 359 embodies the reality that the closest stars are often faint, low-mass objects with complex magnetic behavior. Its discovery and ongoing observation offer insight into stellar evolution, magnetic dynamics, and the challenges inherent in searching for planets around red dwarfs, stars that, by number, make up the bulk of the Milky Way's population. Luyten, 21,185, one of our closest neighbours and its planetary puzzle. Among the roster of nearby stars, Luyten, 21,185, holds a position of prominence for both its proximity to the Sun and its historical significance in the search for exoplanets. Located roughly 8.31 light-years away, it is one of the closest stars to Earth, yet it remains too faint to be seen without a telescope. The star's designations reflect its entries in catalogues rather than common names. It is listed in the Lalande catalogue, a star catalogue compiled by French astronomer Jérôme Lalande in the late 18th century. Luyten 21,185 is a red dwarf of spectral class M2, larger and more luminous than Wolf 359, but still significantly dimmer than the Sun. Its surface temperature is approximately 3,400 to 3,500 Kelvin, and its mass is about 46% that of the Sun. This places it among the mid-range of red dwarfs, not as extreme as Wolf 359, but still cooler and less massive than stars like Alpha Centauri or Sirius. The star achieved prominence in the late 20th century when astronomers began to detect subtle irregularities in its motion that could indicate the gravitational influence of one or more orbiting planets. In the 1990s, high-precision radial velocity measurements suggested the presence of a possible companion, leading to significant excitement in the astronomical community. At the time, detecting planets around red dwarfs was a new frontier, and Luyten 21,185 appeared to be one of the first potential host stars. However, the story of Luyten 21,185's proposed planets is complex and in some ways illustrates the challenges of early exoplanet detection. The initial signals indicating planetary companions were difficult to interpret and in some cases proved inconsistent across different observational campaigns. Some studies identified periodic variations that could correspond to a planet with an orbital period of roughly 9 days, while others suggested multiple signals that were hard to reconcile with a stable planetary system. As instrumentation and analysis techniques improved in the 2000s and 2010s, some of the earlier claims were called into question, leading to a period of uncertainty about the existence of planets around Luyten 21,185. Part of this uncertainty arises from stellar activity. Red dwarfs often exhibit noise in their spectral lines due to magnetic activity, spots, and flares, which can mimic or obscure planetary signals in radial velocity data. In recent years, however, further studies have strengthened the case for at least one confirmed exoplanet around Luyten 21,185. Using improved techniques that account for stellar activity and more extensive data sets, astronomers have reported the detection of a planet designated Luyten 21,185b, a super-Earth-sized world with a minimum mass, roughly 3 to 4 times that of Earth. This planet is believed to orbit relatively close to its star, with an orbital period of approximately 12 days, placing it well inside the star's habitable zone, if traditional criteria based on energy received from the star are applied. Yet because Leyland 21,185 is cooler and dimmer than the Sun, its habitable zone lies much closer to the star than Earth does to the Sun. This proximity means the planet receives a level of stellar radiation that could allow moderate surface temperatures if it has a suitable atmosphere. However, as with other red dwarf systems, tidal locking, a state where the same side of the planet always faces the star, is likely. This could produce extreme temperature contrasts between the day and night sides, raising questions about atmospheric dynamics and climate stability. Additional candidate planets have been proposed around Leyland 21,185, but their existence remains unconfirmed due to the difficulty of disentangling stellar noise from true planetary signals. The star's proximity and relatively quiet behaviour compared to more active red dwarfs make it one of the best laboratories for studying low-mass exoplanets and understanding how planetary systems form around stars unlike our own Sun. Leyland 21,185 also highlights the evolution of exoplanet science itself. Early claims of planets around nearby stars often faced skepticism or required revision as techniques matured. Today, the combination of radial velocity data, transit surveys, and statistical analysis allows astronomers to approach these systems with far greater precision, reducing false positives and refining planetary parameters. Leyland 21,185 stands as a testament to this progression, from tentative early signals to a clearer picture of at least one nearby super-Earth. Sirius, the brightest star in the night sky with a hidden companion. Unlike Wolf 359 and Leyland 21185, Sirius needs no telescope at all. It is the most luminous star in the night sky and has been familiar to humanity for millennia. Located approximately 8.60 light-years away, Sirius dominates the winter skies of the Northern Hemisphere, shining with a brilliance unmatched by any other star visible from Earth. Sirius, also known as the Dog Star, has a rich presence in human culture and mythology. Ancient civilizations associated Sirius with seasonal changes, agricultural cycles, and spiritual significance. It is referenced in Egyptian, Greek, and Polynesian traditions, often representing light, power, or the arrival of significant astronomical events. Despite its brightness, Sirius is not a single star, but a binary system, consisting of Sirius A and a faint compact companion known as Sirius B. Sirius A is a white main sequence star of spectral class A1b, meaning it is larger, hotter, and more massive than the Sun. With a surface temperature of roughly 9,400 Kelvin, Sirius A emits intense visible light, making it prominent despite its modest proximity compared with closer but faint red dwarfs. Sirius B, in contrast, is a white dwarf, the dense remnant of a once massive star that exhausted its nuclear fuel and collapsed under gravity. White dwarfs pack a mass comparable to the Sun's into a volume similar in size to Earth's. They no longer undergo fusion, but remain hot and luminous due to residual thermal energy slowly radiating away over billions of years. The existence of Sirius B was first inferred in the mid-19th century when astronomers noticed irregularities in Sirius A's motion. British astronomer Friedrich Bessel detected subtle deviations in the position of Sirius A that could only be explained by the gravitational influence of an unseen companion. This prediction was confirmed in 1862 when American astronomer Alvan Graham Clark directly observed Sirius B through a telescope, making it one of the earliest white dwarfs ever discovered. Sirius A and B orbit each other with a period of approximately 50 years, with their separation varying from about 8.1 to 31.5 astronomical units over the course of each orbit. This orbital dance has been studied for over a century, providing one of the best measured binary systems in modern astrophysics. The precise tracking of Sirius A's motion has allowed astronomers to calculate the mass of Sirius B with remarkable accuracy, confirming theoretical predictions about white dwarf structure and the limits of electron degeneracy pressure, the quantum mechanical force that prevents white dwarfs from collapsing into black holes. Despite its prominence and detailed study, no confirmed exoplanets have been detected around Sirius A or B. The intense brightness of Sirius A makes detecting small orbiting bodies extremely difficult, using standard methods such as radial velocity or transit photometry. Likewise, Sirius B's faintness and proximity to the much brighter primary complicate efforts to observe any accompanying objects. However, the possibility of planets in the Sirius system has not been entirely ruled out. Models of binary star formation suggest that planets could form either close to the primary star or in wider circumbinary orbits, provided that gravitational interactions do not destabilize their paths. Future observational campaigns using advanced direct imaging and interferometry techniques may yet reveal worlds in this iconic system. Sirius's cultural significance extends to its role in modern astronomy as well. Because of its brightness and well-characterized orbit, Sirius has served as a calibration source for telescopes and instruments studying stellar atmospheres, binary dynamics, and evolution. Its white dwarf companion provides a laboratory for testing theories of matter at extreme densities, helping refine models of stellar endpoints and informing our understanding of the fate of stars like the Sun. The last star in this chapter, Luyten star, represents a class of nearby red dwarfs that have become central to the contemporary search for exoplanets. Located at approximately 12.36 light-years from Earth, Luyten star is not the very closest, but it still counts among the closest 24 stellar neighbours. Its practical importance lies in both its physical properties and its role in advancing exoplanet detection techniques. Luyten star is named after Willem Jacob Luyten, a Dutch-American astronomer whose work in the mid-20th century focused on high proper-motion stars. Luyten compiled extensive catalogues that identified nearby stars based on their motion across the sky, a method that successfully uncovered many low-mass, dim stars, like the one that now bears his name. Luyten's contribution remains foundational to the ongoing effort to map our stellar neighbourhood. Classified as a red dwarf of spectral type M3.5v, Luyten star is cooler and less massive than the Sun, but larger and more luminous than the smallest red dwarfs such as Wolf 359. Its surface temperature of approximately 3,400 Kelvin and moderate luminosity make it a favourable target for exoplanet searches, because its lower mass means that planetary signals, the small wobbles induced by orbiting bodies, create relatively larger effects on the star's motion. In 2014, an international team of astronomers announced the discovery of a planet orbiting Luyten star using the radial velocity method, designated Luyten b, also known as GJ273b. This exoplanet has a minimum mass of approximately 2.89 Earth masses and orbits within the inner portion of its star's habitable zone, with a period of about 18 days. This places it in a region where surface temperatures might allow liquid water to exist on a rocky world, provided the planet has a suitable atmosphere. The discovery of Luyten b was significant because it demonstrated that potentially temperate, low-mass planets could be detected around nearby red dwarfs, even with current observational capabilities. The relatively short orbital period and the star's calm activity level, compared to more flare-prone dwarfs, made it easier to isolate the planetary signal from stellar noise. Additional candidate planets suggested by the same data include a second super-Earth with a minimum mass around 1.18 Earth masses and an orbital period of 4.7 days, though confirmation of this inner candidate remains tentative. Mid-range stars in the Milky Way. Once we move beyond the handful of stars clustered within 10 or 20 light-years of Earth, the Milky Way begins to reveal its true scale. This is the region where distance stops being an abstract number and becomes a logistical barrier that reshapes every assumption about interstellar travel. Stars between 50 and 500 light-years away are not remote by galactic standards, yet they exist far beyond the reach of anything humanity has ever built or launched. They are close enough to be studied in extraordinary detail, close enough to host some of the most intensively searched planetary systems known, but far enough that even the most optimistic propulsion concepts struggle to compress travel times into anything resembling a human time frame. This mid-range stellar zone is where astronomy transitions from nearby neighbours to the broader local neighbourhood of the Milky Way. It includes stars visible to the naked eye, stars that anchor constellations humans have recognised for thousands of years, and stars that have become central to modern exoplanet science because they sit at the intersection of accessibility and abundance. Tau Ceti, Epsilon Eridani, Vega and Fomalhaut are not obscure catalogue entries. They are among the most studied stars in the sky, precisely because they occupy this critical middle distance. Understanding what it would take to reach them requires more than listing speeds and distances. It requires placing each star into context, how far it truly is when measured against the fastest objects ever created by humanity, how theoretical propulsion systems compress or fail to compress that distance, and how even fractions of light speed radically change the meaning of interstellar travel. This is where time, not distance, becomes the dominant obstacle. Within 50 light-years, stars are close enough that interstellar travel still feels like a stretch, but not an impossibility on cosmic timescales. Once distances extend beyond that boundary, however, the numbers begin to scale faster than intuition can comfortably handle. 50 light-years is already nearly 12 times farther than Alpha Centauri. 500 light-years is more than 100 times farther. At these distances, even optimistic propulsion concepts that dramatically outperform chemical rockets still demand centuries, millennia, or longer. This range also represents a dense slice of the Milky Way's stellar population. Because the galaxy is shaped like a flattened disk, stars are not evenly distributed in all directions. Looking outward along the plane of the galaxy, the number of stars rises rapidly with distance, meaning that within a few hundred light-years, we are already sampling tens of thousands of stellar systems. Many of these stars are sun-like or slightly smaller, making them prime candidates for planet formation, debris disks, and long-term stability. From an observational standpoint, stars in this range are close enough that astronomers can measure their masses, compositions, rotation rates, and circumstellar environments with high precision. From a travel standpoint, however, they are far enough that every kilometre per second gained in velocity matters enormously, because small changes in speed translate into differences of thousands or tens of thousands of years in travel time. This is the scale at which Voyager-class speeds become effectively useless for interstellar exploration. Nuclear propulsion becomes merely incremental rather than transformative, and only relativistic concepts begin to produce timelines that fall within historical rather than geological epochs. Tau Ceti is one of the most compelling stars in the mid-range category precisely because of how familiar it appears. Located at a distance of approximately 11.9 light-years, it technically sits closer than the lower bound of 50 light-years, but it serves as a bridge between the immediate stellar neighbourhood and the broader mid-range population due to its scientific importance and the depth of study devoted to it. Tau Ceti is a G-type main sequence star, slightly smaller and dimmer than the Sun, with a long-term stability that has made it a benchmark for comparisons with our own solar system. Tau Ceti has been studied for decades as a potential host for habitable planets, in part because its low stellar activity suggests a relatively calm radiation environment. Unlike many red dwarfs, it does not produce frequent, violent flares, and its luminosity has remained stable over billions of years. Observations have revealed a massive debris disk surrounding the star, far more substantial than the Kuiper belt in our own solar system, indicating an active history of planet formation and collisions. Radial velocity measurements suggest the presence of multiple planets, including several super-Earth candidates, some of which may orbit within or near the star's habitable zone. While the exact configurations remain under refinement, Tau Ceti has become one of the most frequently cited examples of a nearby Sun-like system that could plausibly host long-lived rocky worlds. From a travel perspective, Tau Ceti illustrates how even the closest Sun-like stars remain unreachable with current technology. At Voyager, one speed of roughly 17 kilometers per second, a spacecraft would require on the order of 210,000 years to reach Tau Ceti. This is not a mission duration, it is an evolutionary timescale. Human civilizations rise and fall on far shorter cycles. With advanced nuclear thermal propulsion or fusion-based concepts that might achieve speeds 10 to 20 times greater than Voyager, travel times compress to 10,000 to 20,000 years, still far beyond any practical human endeavour. Even with optimistic light sail concepts approaching 10% the speed of light, Tau Ceti would remain nearly 120 years away, making it one of the closest stars reachable within a single human lifetime only under speculative and unproven technologies. Tau Ceti demonstrates a crucial lesson of mid-range stars. Proximity, in astronomical terms, does not translate to accessibility in human terms unless velocities approach relativistic scales. Epsilon Eridani, located approximately 10.5 light-years from Earth, is another star often grouped with nearby systems. Yet its characteristics and scientific role place it firmly within the conceptual framework of mid-range travel challenges. Slightly smaller and cooler than the Sun, Epsilon Eridani is significantly younger, estimated to be only 400 to 800 million years old, compared to the Sun's 4.6 billion years. This youth makes Epsilon Eridani a dynamic system, still actively evolving, with a pronounced debris disk and evidence of ongoing planetary formation processes. Observations have revealed multiple belts of dust and debris, suggesting the presence of planets shaping these structures through gravitational interactions. At least one confirmed gas giant, Epsilon Eridani b, orbits the star at a distance comparable to Jupiter's orbit around the Sun. The system's relative proximity and activity have made it one of the most intensively studied stellar environments outside our own. It offers astronomers a rare opportunity to observe planetary system evolution in a relatively early stage, providing insight into how our own solar system may have looked billions of years ago. Travel times to Epsilon Eridani reinforce the same pattern seen with Tau Ceti. At Voyager speed, the journey would take approximately 180,000 years. Even with fusion propulsion capable of reaching 1% the speed of light, travel would still require over 1,000 years. Only at velocities approaching 10 to 20% of light speed do timelines compress into the range of 50 to 100 years. A duration that still presents immense engineering, biological, and societal challenges. Epsilon Eridani highlights another reality of mid-range stars. Many of the most scientifically valuable systems are not the most stable or tranquil. Youth brings activity, radiation, and gravitational complexity, all of which complicate both observation and hypothetical exploration. Vega, a bright anchor in the local galactic disk. Vega, located approximately 25 light-years from Earth, occupies a unique position in human astronomy. It is one of the brightest stars in the night sky and has served as a photometric reference point for measuring stellar brightness for generations. Vega is an A-type star, significantly more massive and luminous than the Sun, rotating so rapidly that it is visibly flattened at the poles. The star's brightness and proximity have allowed astronomers to study its structure in remarkable detail. Vega also possesses a debris disk, first detected in the 1980s, which provided some of the earliest evidence that planetary systems may be common around stars beyond the Sun. The disk suggests the presence of planetesimals and possibly planets shaping the surrounding material, though no confirmed planets have yet been directly observed. Despite its visibility, Vega is a challenging destination from a travel perspective because its mass and radiation environment differ substantially from the Sun's. A-type stars have shorter lifespans, often burning through their nuclear fuel in hundreds of millions, rather than billions of years, raising questions about long-term habitability around such stars. At Voyager speeds, reaching Vega would require approximately 450,000 years. Even at 10% the speed of light, the journey would still take 250 years, underscoring how rapidly travel times escalate once distances extend beyond the immediate stellar neighborhood. Vega's role as a navigational and observational anchor does not translate into accessibility. It remains a destination far beyond realistic reach without relativistic propulsion. Fomalhaut, located approximately 25 light-years away, is another bright, massive star surrounded by a complex debris disk. Classified as an A-type star, Fomalhaut is younger and more luminous than the Sun, with a massive circumstellar disk that has been imaged directly in extraordinary detail. The system gained widespread attention with the announcement of a directly imaged object, initially designated Fomalhaut B. Subsequent observations revealed that this object was not a conventional planet, but likely a cloud of debris resulting from a massive collision between planetary bodies. This discovery transformed Fomalhaut into a case study for the violent processes that shape young planetary systems. From a travel standpoint, Fomalhaut mirrors Vega. Voyager-class probes would require nearly 450,000 years to arrive. Nuclear or fusion propulsion could reduce that to tens of thousands of years, while relativistic concepts might compress the journey into a few centuries at best. Fomalhaut illustrates another mid-range reality. Many stars in this distance range host dynamically active systems where planets are still migrating, colliding, or reshaping their environments. These are not static destinations, but evolving systems, meaning that any journey spanning centuries or millennia would arrive at a system significantly altered from the one initially observed. If one could visualize these journeys on a timeline rather than a map, the scale becomes unmistakable. At Voyager speed, all stars in the 50 to 500 light-year range effectively collapse into the same category, unreachable within any meaningful human context. Whether a star is 50 or 500 light-years away, the difference between hundreds of thousands and millions of years becomes academic rather than practical. Nuclear thermal or fusion propulsion introduces differentiation, compressing travel times by 1 or 2 orders of magnitude, but still leaving most destinations beyond historical timescales. Only light-speed fractions fundamentally reshape the problem, transforming millennia into centuries and centuries into decades. Even then, these journeys demand technologies that do not yet exist, energy budgets that dwarf global production, and solutions to challenges ranging from radiation exposure to interstellar dust impacts at relativistic velocities. The mid-range stars of the Milky Way are close enough to tempt us with detail, but far enough to remind us that interstellar travel is not simply an extension of spaceflight. It is an entirely different category of endeavour. Tau Ceti, Epsilon Eridani, Vega, and Fomalhaut collectively define the boundary between observational astronomy and physical exploration. They are close enough to study, to map, and to understand in remarkable detail, yet far enough that reaching them requires breakthroughs that redefine propulsion, energy, and time itself. This region of the galaxy strips away the illusion that proximity equals accessibility and replaces it with a more sobering truth. The Milky Way is vast not because of distance alone, but because of time. In the mid-range zone, time becomes the dominant currency, and without speeds approaching that of light, it is a currency humanity cannot afford. Exoplanet discoveries, habitable zone worlds, and why these stars matter. The modern era of astronomy has transformed the search for planets from speculation into measurement. For most of human history, planets beyond the solar system were an abstract idea, debated philosophically rather than studied scientifically. That changed only in the last few decades, when advances in instrumentation allowed astronomers to detect minute signals embedded in starlight, tiny wobbles in stellar motion, slight dimmings in brightness, subtle shifts in spectra that revealed the presence of orbiting worlds. As detection methods improved, attention increasingly focused on one specific category of planets, those located in the habitable zones of their stars, where temperatures could allow liquid water to exist on a planetary surface under the right atmospheric conditions. Habitable zone exoplanets are not defined by habitability itself, but by energy balance. They occupy orbital regions where stellar radiation is neither so intense that surface water would boil away, nor so weak that it would freeze permanently. This definition is deliberately narrow and physical rather than biological. It does not assume life, intelligence, or Earth-like conditions. It simply identifies places where chemistry as we know it could plausibly proceed in liquid water, making these planets the most scientifically valuable targets for understanding planetary evolution, atmospheres, and the potential prevalence of life-supporting environments in the Milky Way. The stars that host these planets are not random. Certain stellar types are more likely to be studied, more likely to yield detectable planets, and more likely to support stable habitable zones over long timescales. The stars discussed throughout this documentary, nearby and mid-range stars such as Tau Ceti, Epsilon Eridani, Luyten star, and others, have become central to exoplanet research precisely because their physical properties make them ideal laboratories for answering fundamental questions about planets beyond our solar system. Early exoplanet discoveries were dominated by massive gas giants orbiting extremely close to their stars. These hot Jupiters were not expected to exist based on solar system models, but they were the easiest planets to detect because their large masses and short orbital periods produced strong signals. As detection sensitivity improved, astronomers began uncovering smaller planets at greater distances from their stars, including rocky worlds and super-Earths orbiting within habitable zones. The launch of dedicated space missions marked a turning point. Space-based observatories designed to monitor stellar brightness with extraordinary precision allowed astronomers to detect planets only slightly larger than Earth. These missions revealed that small planets are common and that many stars host multiple planets, often arranged in compact systems very different from our own. Statistical analysis of these findings demonstrated that habitable zone planets are not rare exceptions, but a frequent outcome of planet formation. As a result, the focus of exoplanet science shifted from asking whether habitable zone planets exist to asking what kinds of stars host them, how stable these environments are, and how planetary atmospheres behave under different stellar conditions. This shift elevated certain nearby and mid-range stars into priority targets, not because they are the closest or brightest, but because they provide the clearest opportunities to combine detection, characterization, and long-term observation. Habitable zones and stellar type. The location and stability of a habitable zone depends strongly on the star's mass, luminosity, and activity. Around Sun-like stars, habitable zones are located at distances comparable to Earth's orbit, with orbital periods measured in months or years. Around smaller, cooler stars, particularly red dwarfs, habitable zones are much closer in, often with orbital periods of days or weeks. This proximity creates both advantages and challenges. Planets in close-in habitable zones are easier to detect because they orbit more frequently, producing more data in a shorter time. Their gravitational influence on the star is stronger, and their transits occur more often, making confirmation faster. At the same time, close proximity exposes these planets to stellar activity, including flares, radiation bursts, and particle winds that can erode atmospheres over time. Stars like Luyten star and other nearby red dwarfs have therefore become focal points for exoplanet research. Their habitable zones are compact, detectable, and accessible to current instruments, yet their long lifespans, often trillions of years, offer the possibility of extended periods of planetary stability. Understanding whether habitable zone planets around these stars can retain atmospheres is one of the central questions in modern astrophysics. Sun-like stars such as Tau Ceti occupy a different category. Their habitable zones are farther out and more stable in terms of radiation environment, but the longer orbital periods make detection slower and more difficult. Nevertheless, when habitable zone planets are identified around these stars, they provide the closest analogues to Earth-like conditions, making them invaluable for comparative planetology. In recent years, the catalogue of confirmed and candidate habitable zone exoplanets has expanded rapidly. Improved radial velocity techniques have reduced noise from stellar activity, allowing astronomers to isolate planetary signals with unprecedented precision. At the same time, long-duration transit surveys have accumulated years of continuous data, enabling the detection of planets with longer orbital periods. Several nearby stars have yielded particularly important results. Around red dwarfs, multiple systems have been found to host planets within or near their habitable zones, often with masses between 1 and 4 times that of Earth. These discoveries have challenged earlier assumptions that red dwarf systems would be hostile to planetary habitability due to intense stellar activity. Instead, evidence suggests that some red dwarfs exhibit quieter phases or possess magnetic configurations that reduce long-term atmospheric loss on orbiting planets. Around Sun-like stars, the pace of discovery has been slower but equally significant. Candidate habitable zone planets detected through subtle radial velocity signals have begun to fill in the gap between theoretical models and observational evidence. While confirming these planets remains challenging, their existence supports the idea that Earth-sized worlds in temperate orbits may be common throughout the galaxy. In addition to new detections, reanalysis of older data has played a major role. As statistical methods improve, astronomers revisit archival observations to extract signals that were previously indistinguishable from noise. This has led to the confirmation of planets that were once considered ambiguous and has refined estimates of planetary masses and orbits. Not all stars are equally valuable for exoplanet research. The stars that attract the most attention are those that allow scientists to move beyond detection and toward characterization. This includes measuring planetary mass, radius, density, and eventually atmospheric composition. Stars that are relatively close, bright and stable provide the best opportunities for this deeper level of study. Proximity matters because signal strength decreases with distance. The closer a star is to Earth, the stronger the planetary signals appear in observational data. This is why nearby stars, even those that are faint to the naked eye, dominate exoplanet research. A planet orbiting a star 10 light-years away produces a signal that is orders of magnitude easier to study than an identical planet orbiting a star hundreds of light-years distant. Stellar stability is equally important. Stars with low levels of magnetic activity produce cleaner data, making it easier to separate planetary signals from stellar noise. This is one reason Tau Ceti and similar stars receive sustained attention. Their relatively calm behaviour over long timescales allows astronomers to accumulate precise measurements without constant interference from flares or spots. The structure of planetary systems also plays a role. Stars with multiple planets provide opportunities to study planetary interactions, migration histories, and resonance effects. When one of these planets lies in the habitable zone, it becomes possible to place that world within a broader system-wide context, revealing how its environment has evolved over time. Atmospheres and the next phase of study. Detecting a planet in the habitable zone is only the first step. The next challenge is understanding what that planet is actually like. This requires studying planetary atmospheres, which hold clues to surface conditions, climate, and chemical processes. Certain stars are better suited for this than others. Red dwarfs offer advantages because their small size makes planetary transits more pronounced, allowing astronomers to analyze starlight filtered through a planet's atmosphere during transit events. This technique, known as transmission spectroscopy, can reveal the presence of molecules such as water vapor, carbon dioxide, methane, and oxygen under favorable conditions. Sun-like stars present a greater challenge due to their larger size and brightness, but they also provide a more familiar context for interpreting atmospheric data. A habitable zone planet around a Sun-like star can be compared directly to Earth in terms of energy balance and orbital geometry, making it a key reference point for understanding habitability in a broader sense. The stars highlighted in this documentary occupy a crucial middle ground. They are close enough to allow detailed study, diverse enough to represent multiple stellar classes, and stable enough to support long-term observational campaigns. As a result, they are likely to remain central to exoplanet research for decades to come. Even when habitable zone planets are ultimately found to be inhospitable, their scientific value remains enormous. Studying why a planet failed to retain an atmosphere or why its climate evolved in a particular direction provides insight into planetary physics and atmospheric chemistry. These lessons apply not only to exoplanets, but also to the history of Earth, Mars, and Venus. Stars with well-characterized habitable zone planets allow astronomers to test models of atmospheric escape, magnetic shielding, and planetary geology under conditions that differ from those in the solar system. They also help refine estimates of how common Earth-like conditions may be across the galaxy, a question that underpins much of modern astrophysics. Reaching the galactic core. The centre of the Milky Way is not a symbolic destination or a metaphorical heart. It is a physically real, densely packed, violently energetic region of space, located roughly 26,000 light-years from Earth, buried behind vast clouds of interstellar dust and gas that render it invisible to ordinary optical telescopes. Everything we know about it has been pieced together through radio waves, infrared observations, X-ray detections, and decades of careful motion tracking of stars whose paths betray the gravitational presence of something extraordinarily massive. This region is not merely far in terms of distance. It exists in a different astrophysical regime altogether, where gravity, radiation, density, and time itself behave in ways fundamentally unlike the quiet stellar neighborhoods near the Sun. To talk about reaching the galactic core is to confront the ultimate practical limits of interstellar travel inside our own galaxy. Unlike the nearest stars, whose distances stretch human engineering but remain conceptually graspable, the galactic center pushes travel times beyond historical, biological, and even civilizational scales. It is not simply another destination on a longer map. It represents a transition point where conventional assumptions about propulsion, shielding, navigation, and survival cease to apply in any straightforward way. At the exact dynamical centre of the Milky Way lies Sagittarius A star, a compact radio source that marks the location of a supermassive black hole with a mass of approximately 4 million times that of the Sun. This object does not dominate the galaxy by size, but by gravitational influence. Its event horizon is smaller than the orbit of Mercury, yet its gravity governs the motion of stars across a region spanning light years. Sagittarius. A star was not discovered visually, but inferred through motion. Beginning in the late 20th century, astronomers used infrared telescopes to track individual stars orbiting an apparently empty point in space. These stars, some moving at thousands of kilometers per second, followed tight elliptical orbits that could only be explained by an unseen mass far greater than any cluster of normal stars. Decades of observations confirm not only the existence of the black hole, but also its precise mass and location with extraordinary accuracy. Surrounding Sagittarius A star is a dense stellar environment known as the nuclear star cluster, containing millions of stars packed into a region only a few dozen light years across. Many of these stars are massive, young and short-lived, forming in an environment that appears hostile to star formation by conventional standards. The intense tidal forces near the black hole should, in theory, prevent gas clouds from collapsing, yet observations show that star formation persists, suggesting exotic and poorly understood processes at work. Beyond the immediate vicinity of the black hole lies the central molecular zone, a vast reservoir of gas and dust, extending hundreds of light years. This region is a site of intense star formation, supernova explosions, and high-energy phenomena. Magnetic fields are stronger here than in the galactic disk. Cosmic ray densities are elevated, and radiation levels far exceed those found near the Sun. The galactic core is not a static structure, but a continuously evolving environment shaped by gravity, turbulence, and energy feedback on enormous scales. A distance of 26,000 light years is easy to state, and extraordinarily difficult to internalize. Light itself, moving at approximately 300,000 kilometers per second, requires 26,000 years to cross the space between Earth and the galactic center. Every photon detected from Sagittarius A star today began its journey before the earliest human civilizations built permanent cities. At the speed of Voyager 1, humanity's fastest object to escape the solar system, reaching the galactic core, would require on the order of 450 million years. This is longer than the time since complex life first emerged on Earth. Continents would rearrange themselves repeatedly, species would rise and go extinct, and the Sun itself would undergo significant evolutionary changes long before such a probe arrived. Even with nuclear thermal propulsion or fusion-based systems capable of reaching velocities tens or hundreds of times greater than Voyager, travel times would still fall in the range of millions to tens of millions of years. These are not mission durations, they are geological epochs. At such scales, the destination itself cannot be assumed to remain the same. Stars would migrate, explode, or be consumed, and the structure of the galactic core would evolve substantially during the journey. Only when velocities approach a significant fraction of the speed of light do travel times begin to compress into something remotely resembling meaningful durations. At 10% of light speed, the journey would still require approximately 260,000 years as measured from Earth's frame of reference. At 50% of light speed, the time drops to about 52,000 years, still far beyond any conceivable human timescale. Even at 99% of light speed, the journey remains tens of thousands of years long in the external frame, though relativistic time dilation would reduce the experience time aboard the spacecraft to a few thousand years. The galactic core is therefore not merely distant. It is temporally separated from us in a way that fundamentally alters the nature of exploration. Challenges of travel. Distance is only the beginning. Distance alone would be enough to render travel to the galactic core unrealistic, but it is far from the only obstacle. The path between the solar system and the core is not empty. It is filled with the interstellar medium, a diffuse mixture of gas, dust, charged particles, magnetic fields, and cosmic radiation that becomes progressively denser toward the center of the galaxy. At relativistic speeds, even individual hydrogen atoms become lethal projectiles. A collision with a particle at near light speed releases energy comparable to high-energy radiation, capable of damaging or destroying spacecraft materials. Shielding against this environment would require unprecedented mass, advanced electromagnetic deflection systems, or entirely new approaches to spacecraft design. Radiation exposure increases dramatically as one moves inward through the Milky Way. The density of cosmic rays, supernova remnants, and energetic particles rises toward the core. Near Sagittarius, a star, X-ray and gamma-ray emissions are common, originating from accretion events, stellar winds, and high-energy interactions within the dense stellar environment. A spacecraft traveling through this region would face continuous radiation bombardment far exceeding anything experienced in interplanetary space. Gravitational hazards also become significant. The galactic core is crowded. Stars pass relatively close to one another, increasing the risk of gravitational perturbations that could alter trajectories over long timescales. Navigation in such an environment would require constant correction and precise modelling of gravitational influences from multiple massive objects. Additionally, the sheer density of stars introduces collision probabilities that, while still small on human scales, become non-negligible over journeys lasting tens or hundreds of thousands of years. Interstellar travel to the core would not be a straight line through empty space, but a dynamic traversal through an evolving gravitational landscape. Reaching the galactic core does not imply approaching the black hole itself. Sagittarius A star is not a destination in the conventional sense. The region near the event horizon is dominated by extreme gravity and tidal forces that would destroy conventional spacecraft long before arrival. Instead, any realistic mission would target stars orbiting within tens or hundreds of light-years of the core, using them as observational platforms to study the central environment. Stars near the core experience conditions radically different from those near the Sun. Their orbits are often highly elliptical, influenced by both the central black hole and the surrounding mass distribution. Many of these stars move at velocities thousands of times faster than the Sun's orbital speed around the galaxy. Some complete full orbits around Sagittarius A star in just a few decades. From a scientific standpoint, these stars are invaluable. They provide direct tests of general relativity in strong gravitational fields, insights into stellar evolution under extreme conditions, and evidence of how supermassive black holes interact with their environments. From a travel standpoint, however, targeting such stars adds layers of complexity to navigation, rendezvous, and long-term stability. But you may ask, could humans ever target the core? You see, any discussion of missions to the galactic core necessarily enters speculative territory. Even the most optimistic propulsion concepts proposed by theoretical physics face energy requirements that exceed current or foreseeable technological capabilities by many orders of magnitude. Concepts such as fusion-powered relativistic ships, antimatter propulsion, or beamed energy light sails could, in principle, accelerate small payloads to a fraction of light speed. Projects like Breakthrough Starshot envision gram-scale probes reaching nearby stars within decades, but scaling such concepts to carry humans, life support systems, shielding, and deceleration mechanisms is an entirely different problem. Deceleration is a particularly severe challenge. Accelerating to relativistic speeds is only half the journey. Slowing down upon arrival requires either carrying vast amounts of fuel, relying on external infrastructure that does not exist, or using complex interactions with interstellar media or stellar radiation fields. Near the galactic core, the chaotic environment complicates any attempt at controlled braking. Even if propulsion and shielding challenges were overcome, mission duration remains prohibitive. Generational ships, cryogenic suspension, or digital consciousness transfer are often invoked in speculative discussions, but each introduces profound, unresolved scientific and engineering questions. A mission lasting thousands of years would not merely transport humans through space. It would transport an evolving society, subject to cultural drift, biological change, and unforeseen risks. Travel times with ultra-fast theoretical ships. To illustrate the scale involved, consider hypothetical travel times under increasingly extreme assumptions. At 1% of light speed, reaching the galactic core would require approximately 2.6 million years. At 10%, the time drops to 260,000 years. At 50%, 52,000 years. At 99%, roughly 26,000 years in the galactic frame, with experience time on board reduced by relativistic effects to a few thousand years. These numbers assume uninterrupted acceleration, perfect shielding, and flawless navigation, none of which are realistic given known physics. They also assume that the destination remains relevant after tens of thousands of years, an assumption that becomes increasingly fragile as timescales lengthen. The galactic core is dynamic. Star formation rates fluctuate, gas flows evolve, and Sagittarius A star itself undergoes periods of increased activity when it accretes material. A mission launched today would arrive in a core environment shaped by tens of thousands of years of change, potentially unrecognizable compared to current observations. In practical terms, the galactic core functions as a boundary that defines the limits of what interstellar travel could ever plausibly achieve. It is not merely farther than nearby stars. It exists on a scale where distance, time, and environmental hostility converge to impose absolute constraints. Studying the core remotely has already transformed our understanding of galaxies, black holes, and fundamental physics. Observations of Sagittarius A star have confirmed predictions of general relativity, revealed the prevalence of supermassive black holes in galactic centers, and illuminated the processes that shape galaxy evolution. These discoveries required no spacecraft, only patience, precision, and increasingly sophisticated telescopes. Reaching the galactic core physically would offer diminishing returns compared to its cost and risk. The information gained from in situ exploration would likely be incremental relative to what can be learned through remote observation, simulation, and theoretical modeling. In this sense, the galactic core represents not a failure of ambition, but a reminder that exploration takes many forms, and that distance alone does not define scientific reach. The center of the Milky Way remains one of the most extreme environments accessible to human knowledge without physical travel. Hypervelocity stars. Hypervelocity stars are among the most extreme and revealing objects ever observed in the Milky Way, not because of what they are made of, but because of how violently they have been displaced from their place of origin. These stars are not drifting gently through the galaxy along orderly orbits shaped over billions of years. They are moving fast enough to escape the gravitational grip of the Milky Way entirely, carrying with them a record of catastrophic gravitational encounters that can only occur in the most extreme environments known in galactic astrophysics. Their existence transforms the galactic core from a distant abstraction into an active engine capable of reshaping the stellar population of the galaxy on enormous scales. A hypervelocity star is defined not by its brightness or mass, but by its speed relative to the galaxy. Ordinary stars in the Milky Way orbit the galactic center at velocities on the order of a few hundred kilometers per second. Hypervelocity stars exceed this by a wide margin, reaching speeds of 700, 1,000, or even more than 2,000 kilometers per second, fast enough to overcome the combined gravitational pull of all the stars, gas, and dark matter in the galaxy. Once ejected, these stars do not return. They travel outward through the galactic halo, eventually passing into intergalactic space, becoming permanent refugees of the Milky Way. The idea that stars could be ejected from a galaxy was once purely theoretical. For much of the 20th century, stellar motions were understood largely in terms of stable orbits and slow dynamical evolution. That perspective changed as astronomers began to understand the role of supermassive black holes at galactic centers. The Milky Way's central black hole, Sagittarius A star, with its mass of roughly 4 million suns, is capable of exerting gravitational forces so intense that close encounters can completely rearrange the trajectories of stars. Hypervelocity stars are one of the clearest signatures of this process. The most widely accepted mechanism for producing hypervelocity stars involves a binary star system that wanders too close to the central black hole. In such a system, two stars orbit each other while also orbiting the galaxy. When this binary passes within a critical distance of Sagittarius A star, tidal forces from the black hole overwhelm the gravitational bond between the two stars. One star is captured into a tight orbit around the black hole, while the other is flung outward at tremendous speed. This interaction, known as the Hill's mechanism, converts gravitational potential energy into kinetic energy with extraordinary efficiency. The ejected star leaves the galactic center at a velocity so high that no normal galactic process can slow it down enough to keep it bound. This mechanism immediately explains two key properties of hypervelocity stars. First, their trajectories often trace back to the galactic center when reconstructed through proper motion and radial velocity measurements. Second, many of the earliest discovered hypervelocity stars were young, massive stars, which posed an initial puzzle. Massive stars have relatively short lifespans, often only a few 100 million years. Finding them tens or hundreds of thousands of light years from the galactic center implies not only that they were ejected recently on cosmic timescales, but that the ejection process itself must be efficient and ongoing. As surveys expanded, astronomers began discovering hypervelocity stars of different types, including lower-mass stars that can survive for billions of years. This broadened the scientific importance of the phenomenon. Hypervelocity stars are no longer viewed as rare curiosities, but as a natural consequence of galactic center dynamics. Their numbers provide constraints on how often stars interact closely with Sagittarius A star, how many binary systems exist near the core, and how the stellar population of the inner galaxy evolves over time. The distances reached by hypervelocity stars are staggering. Some known examples are located 50,000 to 100,000 light-years from the galactic center, deep in the Milky Way's halo. Others are on trajectories that will carry them well beyond the visible edge of the galaxy. Because these stars are moving so fast, their current positions represent only a snapshot of an ongoing journey that will continue for hundreds of millions or even billions of years. A hypervelocity star ejected at 1,000 kilometers per second will traverse 1 light-year in roughly 300 years. Over 1 million years, it can cross thousands of light-years, effectively sampling large regions of galactic space in a single stellar lifetime. This makes hypervelocity stars uniquely valuable as probes of the Milky Way's gravitational structure. As they move outward, their paths are subtly altered by the distribution of mass in the galaxy, including dark matter, which does not emit light, but dominates the galaxy's mass budget. By measuring deviations in their trajectories, astronomers can infer how mass is distributed in the galactic halo. In this way, hypervelocity stars act as natural test particles, tracing the invisible architecture of the Milky Way on scales that are otherwise extremely difficult to measure. The study of hypervelocity stars has also reshaped our understanding of the galactic core itself. The presence of these stars confirms that Sagittarius A star is not a passive object sitting quietly at the center of the galaxy, but an active participant in stellar dynamics. The rate at which hypervelocity stars are produced places limits on the density of stars near the core, the prevalence of binary systems, and the history of star formation in that region. It also provides indirect evidence about past events, such as the infall of star clusters or intermediate mass black holes, which could enhance the rate of stellar ejections. Not all hypervelocity stars are necessarily produced by the central black hole. Alternative mechanisms exist, though they appear to be less common. One such mechanism involves supernova explosions in binary systems. If one star in a binary explodes as a supernova, the sudden loss of mass can cause the companion star to be released at high speed. While this can produce fast-moving stars, the velocities achieved are generally lower than those produced by interactions with a supermassive black hole. These stars may reach several hundred kilometers per second, but rarely exceed the escape velocity of the Milky Way, unless additional factors are involved. Another possible mechanism involves interactions between galaxies. When smaller galaxies merge with or pass near the Milky Way, gravitational interactions can accelerate stars to high velocities. Some hypervelocity stars may therefore originate not from the Milky Way's core, but from disrupted satellite galaxies. Distinguishing between these origins requires careful analysis of stellar composition, age, and trajectory. Stars ejected from the galactic center often show chemical signatures consistent with the inner Milky Way, while stars originating from dwarf galaxies may exhibit different elemental abundances. Chemical composition is a crucial diagnostic tool in hypervelocity star research. The inner regions of the Milky Way are enriched in heavy elements due to repeated cycles of star formation and supernova explosions. A star that formed near the core is likely to show higher metallicity than one formed in the outer halo. By analysing the spectra of hypervelocity stars, astronomers can trace their birth environments and test whether their inferred origins match their observed trajectories. This combination of kinematics and chemistry has transformed hypervelocity stars into powerful forensic tools for reconstructing events that occurred millions of years ago in regions we cannot directly observe. The scientific interest in hypervelocity stars extends beyond galactic dynamics into stellar physics itself. Being ejected at such high speeds exposes these stars to environments very different from those experienced by ordinary stars. As they travel through the halo and into intergalactic space, they encounter lower densities of gas and weaker magnetic fields. This isolation can affect stellar winds, mass loss rates, and long-term evolution. Observing how these stars age and change provides insight into how environment influences stellar life cycles. Hypervelocity stars also challenge assumptions about planetary systems. If a star hosting planets were ejected from the galactic center, those planets would accompany it on its journey, becoming intergalactic worlds bound to a single star traveling through near empty space. While no confirmed planets have yet been detected around known hypervelocity stars, the possibility raises profound questions about planetary survival under extreme gravitational interactions. The same encounter that ejects a star could disrupt or strip away planets, or in some cases leave tightly bound inner planets intact. Studying hypervelocity stars may eventually reveal whether planetary systems can survive such violent origins. From the perspective of distance, hypervelocity stars blur the boundary between galactic and intergalactic space. Many are currently located far beyond the main stellar disk, at distances where the Milky Way's structure becomes diffuse and poorly defined. Some are already tens of thousands of light years above or below the galactic plane, moving on trajectories that will never intersect the disk again. These stars are effectively time capsules, preserving information about the galactic centre long after they have left it behind. Their discovery has been enabled by large-scale sky surveys capable of measuring stellar positions and motions with extraordinary precision. By comparing images taken years or decades apart, astronomers can detect tiny shifts in a star's position against the background sky. When combined with radial velocity measurements, these data reveal the full three-dimensional motion of a star. Hypervelocity stars stand out immediately in such datasets, their velocities marking them as extreme outliers in an otherwise orderly distribution. The distances involved also make hypervelocity stars relevant to discussions of interstellar and even intergalactic travel. These stars demonstrate that nature itself can accelerate macroscopic objects to velocities far beyond anything humanity has achieved. While the mechanisms involved are not directly transferable to spacecraft propulsion, they provide proof that such velocities are physically attainable under known laws of physics. The energy source, however, is gravitational on a scale that cannot be replicated artificially. Sagittarius A star acts as a cosmic accelerator, converting the gravitational energy of stars into kinetic energy, with an efficiency no engineered system can match. In a broader sense, hypervelocity stars redefine how we think about the Milky Way as a system. The galaxy is not a closed, static structure. It loses stars over time, flinging them into intergalactic space through interactions at its core and during mergers with other galaxies. Over billions of years, this process contributes to the diffuse population of stars that wander between galaxies, bound to no single system. Hypervelocity stars are the most dramatic examples of this ongoing exchange. Their existence also reinforces the central role of supermassive black holes in shaping galactic evolution. These objects are not merely endpoints of stellar collapse or sources of high-energy radiation. They are active sculptors of stellar populations, capable of redistributing stars across vast distances and influencing the structure of galaxies on the larger scales. Hypervelocity stars are the visible traces of this influence, carrying the imprint of the galactic centre far into the halo and beyond. In studying hypervelocity stars, astronomers are effectively studying the reach of the galactic core. Every such star marks a line drawn outward from Sagittarius A star, a reminder that events at the centre can have consequences tens or hundreds of thousands of light years away. They connect the most extreme gravitational environment in the Milky Way to its most remote outskirts, uniting the galaxy into a single, dynamic system governed by gravity and motion. Hypervelocity stars are not numerous compared to the hundreds of billions of stars bound to the Milky Way, but their scientific impact is disproportionate to their numbers. Each one represents a rare event, a moment when a star passed too close to the most powerful object in the galaxy and was forever changed. Their trajectories encode information about the past, their velocities test our understanding of gravity, and their existence forces us to confront the sheer dynamism of the galaxy we inhabit. In the context of reaching stars and understanding galactic scale, hypervelocity stars occupy a unique position. They are stars that have effectively done the impossible by natural means, traversing distances and escaping gravitational bonds that dwarf human ambitions. They are not destinations to be reached, but messengers, carrying with them evidence of processes that operate on scales far beyond any direct human intervention. Through them, the galactic core announces its presence not only at the centre of the Milky Way, but throughout its vast and ever-changing expanse. The Milky Way is not simply a flat disk of stars, gas and dust punctuated by spiral arms and a dense galactic centre. Surrounding this disk is a vast, diffuse halo, an extended spherical region that contains some of the galaxy's oldest stars and the remnants of its earliest formation processes. Within this halo lie halo stars, ancient metal-poor stars, and globular clusters, dense spherical collections of tens of thousands to millions of stars tightly bound by gravity. Halo stars and globular clusters. Halo stars are remarkable because of their age. Most are over 10 billion years old, dating back to a time when the universe itself was less than half its current age. These stars contain very few elements heavier than helium, the so-called metals in astronomical terms, because they formed before repeated cycles of stellar nucleosynthesis had enriched the interstellar medium with heavy elements. In contrast to sun-like stars in the disk, which contain significant quantities of iron, carbon and other metals essential to planetary formation, halo stars are chemically primitive. Studying them allows astronomers to peer into the chemical composition and conditions of the early galaxy, essentially reconstructing the first generations of star formation. Globular clusters amplify this effect because they are not merely individual stars, but gravitationally bound ensembles numbering from tens of thousands to millions of stars. These clusters orbit the Milky Way's center in the halo on highly elliptical and often inclined trajectories, tracing paths that carry them far above and below the galactic plane. Their stars are almost universally old and metal-poor, though some show evidence of multiple stellar populations formed in slightly staggered epochs. Globular clusters are extraordinarily stable over cosmic timescales. They have survived interactions with the galactic disk, tidal stripping, and encounters with other clusters for billions of years, making them living relics of the galaxy's early assembly. Distances to halo stars and globular clusters vary widely. Some halo stars lie only a few thousand light-years from the Sun, such as those in the inner halo, while others are tens of thousands of light-years away, forming a nearly spherical distribution around the galactic disk. Globular clusters, on the other hand, can be located 10,000 to 120,000 light-years from Earth. For instance, Messier 13, the Great Hercules Cluster, lies approximately 22,000 light-years away, while Omega Centauri, the Milky Way's largest globular cluster, resides roughly 15,800 light-years distant. Other clusters populate the outer halo at distances exceeding 100,000 light-years, brushing the edge of the Milky Way's gravitational influence. The ancient nature of halo stars also makes them scientifically valuable. Their low metallicity suggests that they formed before the Milky Way had fully accreted gas and dust from its surrounding environment. In some cases, halo stars appear to be remnants of dwarf galaxies that merge with the Milky Way, carrying with them the chemical fingerprints and orbital motions of smaller progenitor systems. By tracing these stars, astronomers can reconstruct the history of galactic mergers, identifying which stars were native to the Milky Way and which were captured from external systems. Globular clusters often serve a similar role, acting as fossilized signatures of past accretion events. Their ages, motions, and chemical compositions can reveal not only the timeline of cluster formation, but also the dynamic history of the Milky Way's halo. From the perspective of interstellar travel, the halo and its clusters present both practical and conceptual challenges. While the nearest halo stars are relatively close on galactic scales, most globular clusters lie far enough away that conventional spacecraft could never reach them in human timescales. Consider Voyager 1, which travels at roughly 17 kilometers per second. To reach Omega Centauri at 15,800 light-years, Voyager would require over 277 million years, a time span that dwarfs human civilization and exceeds the entire span of Homo sapiens' existence. Even faster, theoretical nuclear propulsion systems capable of achieving thousands of kilometers per second would still require millions of years to reach these distant halo stars and clusters. For closer halo stars, travel is comparatively shorter but remains daunting. A star 5,000 light-years away would take Voyager approximately 87 million years to reach, and even at 1% of the speed of light, a journey would still exceed 500,000 years. These figures illustrate a critical point. While halo stars and globular clusters are accessible conceptually and observationally, they are effectively unreachable using any technology remotely feasible today or in the near future. The scientific interest of halo stars and globular clusters, however, is not diminished by these distances. Observational techniques allow astronomers to study them in great detail without leaving the solar system. Halo stars are monitored for chemical signatures that reveal early nucleosynthesis, their motions mapped to reconstruct the Milky Way's gravitational potential, and their variability studied to understand stellar evolution in low metallicity environments. Globular clusters are observed in aggregate, allowing astronomers to study stellar dynamics on scales that dwarf individual star systems. For example, by tracking the motions of stars within a cluster, scientists can infer the distribution of mass, including the presence of dark matter, the effect of stellar remnants like neutron stars and black holes, and the long-term gravitational stability of dense stellar environments. In addition, globular clusters serve as laboratories for extreme stellar interactions. The high stellar density in their cores, sometimes thousands of stars per cubic parsec, means that collisions, close encounters, and the formation of exotic binary systems are far more common than in the Milky Way disk. These interactions produce phenomena such as blue stragglers, millisecond pulsars, and low-mass X-ray binaries, all of which provide insight into stellar evolution under conditions impossible to replicate elsewhere. By studying these systems, astronomers gain a window not only into the ancient Milky Way, but also into fundamental physics, including mass transfer, stellar mergers, and the formation of compact objects. The distances of halo stars and globular clusters also make them important probes of galactic structure and dark matter. As stars and clusters orbit the Milky Way, their paths are subtly altered by the gravitational influence of both visible and invisible mass. Measuring these trajectories enables astronomers to map the Milky Way's dark matter halo, estimating its shape, density profile, and overall mass distribution. Globular clusters are particularly useful in this context because they are massive, long-lived, and widely distributed across the halo, providing multiple independent points of reference. From a temporal perspective, even if humans could develop ultra-fast spacecraft, the travel times to the halo remain profound. Consider a hypothetical fusion-powered ship travelling at 10% of light speed. To reach Omega Centauri, it would take roughly 158,000 years, a duration that dwarfs any conceivable human lifespan or civilization duration. Even reducing the distance to 5,000 light-years would still require 50,000 years, emphasizing that halo stars exist in a regime where interstellar distances exceed human temporal scales, even under optimistic propulsion scenarios. Despite these challenges, the halo is one of the most scientifically rich regions of the Milky Way. Halo stars and globular clusters record the galaxy's formative epochs, provide insight into early star formation and chemical evolution, and reveal the gravitational structure of the Milky Way on vast scales. They demonstrate that the Milky Way is not a simple spiral disk, but a layered, dynamic system with components that differ in age, composition, and kinematics. Observing the halo also offers indirect clues about phenomena beyond our galaxy. Many of the stars in the outer halo may have originated in dwarf galaxies later absorbed by the Milky Way. Globular clusters themselves may represent the stripped cores of these former galaxies. By studying them, astronomers reconstruct not only the history of the Milky Way, but also the broader process of galaxy assembly in the universe. Each halo star and cluster is a fossil record of cosmic accretion, gravitational interaction, and chemical evolution. In practical terms, halo stars and globular clusters provide a bridge between the accessible solar neighbourhood and the far reaches of the galaxy. They occupy intermediate distances that are conceptually reachable, even if not physically traversable, within a human lifetime. Their extreme age and pristine chemical composition offer insight into epochs predating the formation of the Sun, while their orbital motions encode the gravitational influence of dark matter and past galactic mergers. They illustrate how distance and time scales in astronomy dwarf everyday human experience, reinforcing the immensity of the Milky Way and the challenges of interstellar exploration. The Milky Way's halo, populated with ancient stars and globular clusters, represents a repository of cosmic history. Its stars are relics of the galaxy's formation, carriers of chemical information, and test particles tracing the invisible gravitational scaffolding of the galaxy. Travel times to these objects, measured in hundreds of thousands or millions of years, place them firmly beyond the reach of conventional or even near-future spacecraft. Yet their scientific value is immense. Why some stars will remain forever out of reach. Imagine standing on Earth looking up at the night sky. Hundreds of billions of stars twinkle back at you, each a distant sun, each a potential world waiting to be explored. It is an intoxicating thought. You might imagine humanity someday building ships capable of travelling between these stars, visiting distant systems, walking on alien worlds, sending messages to new civilizations. And yet, for all the romance of exploration, the harsh truth of physics and scale looms over us.